you everyone for being here, and in particular, thank to the organizers. So the topic of my talk will be what you read here. It's phase ordering in the Heisey model with space decay interactions. So within this space decay interaction, there are also long-range interactions. So this is in the topic of the conference. And this is on the classical side. I will only refer to classical systems. So this, more or less, this was the title that I thought I delivered to the organizers, in particular to Tommaso. But then on the program, we have this sort of small literature masterpiece. In particular, the best part is here. Not working. So you see this using, it's very clear that we are using something, but what we are really using is not said here. If you want to know what we use, you have to compare the two things, and actually we are using the easing. So this is a sort. And then also there is this redundancy on one dimension, which is probably, due to the fact that if you didn't understand, I will talk of one dimension, but I was so much scared that you could ask me something about 2 or 3 dimensions, that it's better to precise better. This is what how do they call it, the Freud lapsus, or Freudian lapsus. Okay, let me come to the subject. First of all, let me introduce my collaborators, Paolo Politi in Florence, and Eugenio Lipiello in Naples. So in this talk, I will briefly overview what is very well known in the case where you have coarsening or phase ordering with the nearest neighbors. And then in the second part of my talk, I will move to our results when the interaction goes beyond the nearest neighbor. So I will talk about magnets and related things, and this is the phase diagram of a magnet in equilibrium. This is an experimental realization, and basically we have a critical temperature, and below the critical temperature, of course, you have development of magnetization. And okay, so this is for magnets where you have spins which can point up and down, but also, you know, with the same description, you can also describe a gas lattice, which is appropriate for studying the gas-liquid transition, or a binary mixture like a binary of 2 liquids or binary alloys. A binary liquid is like when you mix water or vinegar, let's say, and oil to prepare your salad, and then you look at the demixing of these 2 liquids. Okay, so what I will talk about is the dynamical process that occurs when you prepare your system at high temperature and then you quench it to a temperature below the critical one. It's not working very well. Okay, so in this case, the system is prepared disordered. Let's say spins are disordered, and then they have the problem to go to an ordered state. And the way they do it is, so this is an experiment on a binary fluid, is by creating domains of the 2 phases, water and oil, or spins up and spins down. And then as time goes on, these domains grow or coarsen, and this process in an infinite system remains forever. Okay. So these are other different experimental realizations. These are liquids, binary alloys, different things. We also have a film, hopefully. This is the phase separation of a binary system which is made of 2 kinds of lipids. Okay, you see different shapes, but more or less you always have this coarsening phenomenon. So the models that we will use are discrete models where you have spins. And so this is basically the Heisey model with the difference that you have a coupling constant which decays with the distance between the 2 spins. If you have a nearest neighbor, this is exactly the Heisey model. And this model has to be supplemented with a kinetic rule. Basically, there are 2 main kinetic rules. The first is the so-called non-conserved order parameter. This is the origin of this acronym here. Which is, this is appropriate for magnets. So actually what you do, you pick up a spin, like one of these, okay, this red one, And then you, with some transition rate, this omega, which obeys the tail balance with respect to this energy, you simply flip it. However, if you want to describe like binary fluids or binary alloys, this is not allowed, because it would mean that you change an oil into a water. So what you have to do is, or for a gas lattice, so this is the gas lattice representation, you have to do Kawasaki spin exchange, which means that you pick up a couple of anti-aligned spins, which means a particle and a void in this representation, and then you flip both of them, which means that you move the particle. Okay, so we made our calculation for both these kind of rules, but in this talk, due to time restrictions, I will only speak about the first one. If you want information about the second one, please come to me and we can talk, or you find in the papers. Okay, just to mention that there are also continuous models, which are models like this one, which are basically founded on the Ginzburg-Landau free energy. Then you write some kind of non-conserved or conserved Langevin equation to describe the evolution of the model. Okay, let me come back to the discrete models. If you do a simulation, which we also do, you get this kind of picture for non-conserved and conserved, and you see again the growth of these domains. And the only thing I want to point out is here that if you measure the typical size of these domains, it grows algebraically in both cases. This is for nearest neighbors, but the exponent is different. It's 1/2 for non-conserved case, and it's 1/3 for the conserved case. Okay, another concept that I have to introduce is dynamical scaling, which means simply the following. If you have snapshots of your system at different times, you have this typical size of domain which is increasing from here to there. And dynamical scaling says that basically the only difference between this picture is a magnification of the scale. So if you enlarge a portion of this picture here, in a statistical sense, of course, you get that one, and nothing else is going on in the system, meaning that the morphology is preserved during the evolution. Okay, now we go to 1D, and the 1D case with nearest neighbor was solved by this man here, and in the 63, I guess. So before looking at that, let me mention that in 1D, of course, the critical temperature is 0. So if you want to have coarsening or phase ordering or phase separation, whatever you want to call it, you have to quench to 0 temperature. But you can prove that if you quench to a finite temperature, provided it is sufficiently low, you still see coarsening for a very, very long time. And this is simply because until the size of the domains has reached the coherence length, coarsening goes on, but the coherence length is large, it's like e to the 1 over temperature. So if temperature is small, this coherence length is exponentially large, and you see coarsening for very, very long times. Okay, so Glauber used this transition rate, which after him is called Glauber transition rate. And the facilitation is due to the fact that the variation in energy due to a spin reversal can only take 3 values in 1D. For this reason, the non-linearity of the problem, which is that hyperbolic tangent that you see there, can be mapped or is exactly, it becomes a linear function of the spins, and this allows you to solve the problem analytically. But of course, you cannot do that in D larger than 1, because you don't have only 3 possible values of variation of energy. There are more, so you cannot fulfill this program. Not for conserved order parameter, again, because you flip 2 spins, so there are more values of the energy. And for sure, not when the coupling constant is space decaying. So in all these cases, you have to, you can do simulation or something else. The physical mechanism whereby coarsening occurs is quite simple. So you see here at some time you have some domain. This is in 1 dimension, of course, up and down or red and blue. And so you can map the problem into a problem where you have two kind of particles which correspond to the two kind of interfaces. And then if you are at very low temperature, what happens is simply that these particles, they move in time by doing a random walk. So it may happen that two of them meet, and when they meet, they annihilate. And when they annihilate, the typical size of the domains you see in this picture has grown. So this is the mechanism whereby domain grow and coarsen in one dimension. And clearly, since this is diffusion, it's quite obvious that the exponent will be 1/2. In the conserved case, something slightly different occurs. Actually, if you use the gas lattice description, what you need is a particle to detach from a domain and reach the other one. This is the mechanism. So it has to travel a distance of order L, which is the typical size of the domains. But okay, it can be very easily shown that the probability of being reattached is very large, is 1 minus 1 over L, and the probability to reach the other side is 1 over L. So basically, this problem can be understood as a diffusion process, but with the diffusion constant, which is getting smaller and smaller as L increases. And if you put all together, this is the diffusion constant, you have this law, and this brings immediately to the 1/3 exponent. Okay, so this is with the nearest neighbor. Now let me enter the part of which are the differences which are induced by this space decaying coupling constant. And in the following, so what we did is rather general, but just to fix the ideas, I will concentrate on exponential coupling, which is of course still short range, and algebraic decay, like R to the D is 1 in this case, and sigma is larger than 0. At the end of my talk, I will say something with sigmas between -1 and 0, which is the case of very strong long-range interactions. So, okay, I have to admit that I'm not an expert in long range. I never work on that, and neither my collaborators. So at some point, someone came to me and he said, why don't you look to extended interaction? And to my surprise, I realized that apparently there is not much literature on this. The only well-organized paper is this one by Alambrey and Rutenberg. However, here they use a continuum approach, as you can see here, and they only consider asymptotic stages, whereas I will show you that pre-asymptotically there is a lot of physics which is going on. On the other hand, we use the Heising models, or discrete models, and so this is a little bit of advertising of our 2 papers on the subject. Okay, so let me start with showing you the simulations. So in simulation, this is the case with nearest neighbors, of course non-conserved. So what you see here is what we know already, that after a short transient, everything goes like d to the 1/2, which is Glauber. And let me flash now what happens when you use the exponential coupling with an increasing value of this typical size, capital R. So you see capital R increases from here to here to here to here. So what you see here is there is a plenty of things which are going on that now I want to briefly introduce to. So first of all, let me divide this process into 2 parts. This first part here is what I will call short range, or short times or early regime. And then all the rest is late stage. This is because we have 2 different analytical techniques to investigate these two limits. So let me start with the early. The early is, which is this part here, is something which is basically mean field. So at short times, if the size of the domains is much smaller than this capital R, basically you have that inside an interaction range, you have many, many, many domains, and so the system behaves as in mean field. However, I have to warn you that this is only locally, I mean only inside a size of order R. So it may happen that it breaks the symmetry because it is main field, so in main field very easily the system breaks the symmetry. Let's say it breaks the symmetry up in this part of the system, but then it will break down in another one, so the system is still with average magnetization, which is 0. So this is locally mean field, but globally not. Okay, once you realize this, you can very easily go through the calculation. You replace your Hamiltonian with the mean field one that you see there. Then you write down the equation for the magnetization. There is an equilibrium one. You have convergence to this equilibrium value, which is exponential in mean field. And then, since the spins are independent in mean field, you have a relation between the size of the domains and the magnetization. So you see that since at low temperature the magnetization goes to 1, the equilibrium value is basically 1, this term goes exponentially to 0, which means that the typical size of the domain grows exponentially. This is what you see here. You have this is log, so this is an exponential behavior that you see here. So this is for the early stage. For the later stages, we use this strategy, which is the following. We replace the whole system where there are many, many domains with a simplified system with only 2 domains. Let's say this is with periodic boundary conditions. And the domain is of typical size L. And we ask which is the time for this domain to be closed, to disappear, due to the motion of the interfaces. And then we argue that since you have scaling in your system, at any time there is only, in the system with many domains, at any time there is only one relevant length. So if we find a relation between time and length, if we reverse it, this will give you the behavior of L of t in the real system with many domains. This is, of course, a scaling ansatz. This is not exact, but it can be shown that it works. So if you do this, if the system works, okay, so what you have to do, you have to compute the time to close this domain. So with nearest neighbors, of course, the time to close the domain is L squared, and you get the exponent 1/2 when you reverse it, which is trivial. But when you have extended interaction, this is not longer simple diffusion. You have a sort of force which is pushing this interface. So what you have to do, you write down a convection diffusion equation with the drift and the diffusion coefficient that you can relate to the quantities in your system, in particular to the variation in energy of flipping the spin. And if you do that, you can find out this T of L, this closure time. Then you reverse it, and you get L of T. And what you get is summarized in this transparency here. So from this analytical approach, what you find that initially you have a ballistic regime, which means that basically the interfaces, they only move in one direction. So the typical size of the domains is growing like time here. And we have some bounds inside which this happens. And this is actually this part of the plot. So you see in each curve there is a part where domains grow more or less linearly in time. Then there is a second regime. Oh, what happens here? Sorry for that. Okay. I don't know why it stops. Okay. Then this is followed by another regime, which is logarithmically slow, meaning that the typical size of domains grows like some log of t. And this is what you see here. In this part of the curves, you see this logarithmic, it's very slow behavior, and you put in the appropriate scales, you can really check that it is a logarithm. And then finally, at the very end of the process, you go into the Glauber. So for any value of R, of capital R, eventually you go to the Glauber state. But if you look here, the times to do that, so all these crossover lengths, they diverge in the slow temperature limit. So if you go to the slow temperature, actually this pre-asymptotic regime, they become really huge. Okay, so although I was scared about the questions in larger dimension, I just want to show you, we did some simulation in 2 dimensions, but things are very difficult there because of time limitations, and also analytically it's more or less a mess. But this is just to show you that you can at least get a glimpse of the crossover to the ballistic. So the ballistic would be this one. In order to, of course, we are still far from there. The effective exponent is here, which goes from 1/2 to something which is perhaps going to 1. So in order to see 1, you would need larger values of this capital R, which cannot access numerically. And also we don't have any analytical tool in this case. Now I want to move to the long-range interaction, which means that the coupling constant decaying algebraically. So let me remind you what we had before with the exponential coupling. We had mean field, ballistic, logarithmic, and diffusive regime. Now if you replace your coupling with the algebraic one, the mean field disappears. This is clear because you don't have a range of distances in which basically the interaction is constant, like with the exponential case. Here everything is decaying as a power law, so there is no mean field. Everything is graduated by this algebraic decay. The ballistic is still there. There are some crossover lengths which again diverge in the small temperature limit. The slow behavior is still there, but the form is a little bit changed. It becomes algebraic with this new exponent. And then you have the diffusive stage, but only if sigma is larger than 1. If sigma is smaller than 1, the Glauber stage is suppressed, and you see this anomalous power law behavior forever. And this, it can be shown that this is related to the fact that the model for sigma smaller than 1, already in equilibrium, something different is happening because it starts to have a finite critical temperature. And this reflects into the dynamical counterpart is the fact that this anomalous scaling here is, it becomes asymptotic. Okay, and this is the picture where I show that all these regimes can be observed. For instance, you see the ballistic, you see this power one is this intermediate one, and then eventually you go, if sigma is larger than 1, into the diffusive one, which is the Glauber one. Okay, so far so good. Now just to, since I think my time is about to finish, I want to say a few words of what happens when the interaction is non-integrable, which is the really, let's call it strong long-range limit. So when sigma is in between -1, that would be mean field, and 0. So this is work in progress, so we didn't finish yet. I can only show you some preliminary results or some preliminary understanding. So, okay, in this case, of course, the system is not extensive, but this we can easily cure using the CATS procedure. But most importantly, it is non-additive. And the consequences of that are the following. So suppose you want to plot the magnetization against time in a system with nearest neighbor or with extended interaction, but with this sigma larger than 0. So actually what you have is that some magnetization develops in time, like that. But if you go to larger and larger system, at a fixed time, this magnetization, that before it was like that, is suppressed. So the larger the system is, the smaller the magnetization is developed. And this tells you that the order of these two limits, it does not commute. Indeed, if you take the thermodynamic limit from the very beginning, and then you go to the large time limit, the magnetization is always 0. And this is what we call coarsening. Coarsening is the competition on equal footing of the, okay, I finished, I am about to finish, of the two kind of domains. There is no prevalence of one on the other, and this is because you are interested into this limit. Of course, if you look to the other limit, where you take a finite system and you let time go to infinity, then at some point it will equilibrate, and so the symmetry will be broken. Now, with very long-range interaction, things are radically different. Actually, what it happens with sigma smaller than 0 is that if you have some magnetization and then you increase the system size, the magnetization stays there. It is independent of the system size. So this means that the order of the two limits here is not important. And, and this means, of course, that coarsening is destroyed by this long-range interaction. So everything goes like more or less in mean field, where you have that the system breaks the symmetry from the very beginning, and coarsening is not possible. Okay, since this, as I told you, these are preliminary results, just to be sure to put my hand on the fire, we are sure that this happens for sigma smaller than minus 1/2, but very, very probably for any sigma smaller than 0, this is the picture. Okay, so I think I'm done. These are my conclusions. I showed you that space-dependent interaction profoundly modified the coarsening process, even in the short-range case. There are this wealth of pre-asymptotic behaviors. Also, the last part is that very interaction with strong long-range kill coarsening. And of course, there is much work which remains to be done. Namely, we looked at the behavior of this growing length, but of course one could ask many, many other things like, I don't know, correlation functions, aging, and so on and so forth. Okay, with this, I think I'm done, and I thank you for your attention.
Yeah, questions, please, yeah.
For the case sigma equal to 1,